Hello everyone. In this lecture, I will cover the topic full adder circuitry. So, before the starting of full adder, I will explain first what is the limitation of half adder circuit. As you all are aware, in a digital circuitry, there are two types of adder circuitry. First one is a half adder, second is a full adder. In previous class, I already discussed about half adder circuitry. So, before starting off, I will discuss what is the limitation of a half adder circuit. Okay, so in limitation of half-adder circuit, if we, as you all are aware, half-adder circuitry has only two inputs, and there is no provision to add a carry coming from the lower order bits when two numbers having a multiple bits. What it means? So, for example, I'm considering two numbers A and B of size of multi-bit. Multi-bit, I'm assuming here A and B having a 4 bits. Okay, 1010. Here is 1011. I'm adding these two numbers. So here 0 plus 1 is 1. Some binary addition you perform, 0 plus 1 is 1 on the LSB. So what is carry? यहाँ पे क्या generate हुआ? Try to understand. 0 plus 1 is 1, carry is nothing. That means nothing means in a digital we are saying 0 carry. So at the next stage, how many bits become? 1, 2, 3. So here 3 bits, here 3 information going to add at a time. So half adder can add at a time 2 bits. So at this situation, half adder will be failed. If so, we cannot add here with the help of half adder. So what is a here will be a result? See here 0 plus 1 is 1, 1 plus 1 is 0. So again here carry generated 1. At the next is again, if you see here three numbers A, B. A and B is 0, 0, and here this is 1. This is a carry generated from the lower order bit. So this is carry. This one is carry bit. So again at the next is we having a three numbers. Out of three numbers, two numbers be the this will be a previous carry. So at this situation, half adder will be a fail. So always remember whenever we are adding two numbers of multiple bit, at that time half adder will be fail. That time we require a full adder. Okay. So with the help of half adder, we can add two numbers of size of single bit. In the previous section, I already discussed single bit. That means A and B will be it may be 1 1, it may be 0 1, or it may be 1 0 or 0 0. The single bit को आप ऐड कर सकते हो. But multi bit के more than one bit है यदि A and B में, that time we definitely require a full adder. Okay, the block diagram of full adder. Here are three inputs A, B, C, and two output S and C node. Okay, S here is sum, C node for carry. So first, so truth table of full adder, because full adder circuitry having a three input A, B, C. So with the help of three input, write all possible combination in a truth table. So I written here first all possible combination for inputs. So what will be sum? If we are performing a sum, so A plus B, if any previous carry is coming, in तीनों को you add here. तो 0 plus 0, sum will be a 0. क्या carry generate हुआ? Nothing carry, that means 0. If you here add A, B, C, here 0 plus 0 plus 0 is 0, and 0 plus 1 is 1. So sum will be 1 and carry will be here 0. Similarly here you add 0 plus 1, result will be here 1. 1 plus 0 is 1. Sum is 1, carry is 0. Now next one is 0 plus 1 is sum यहाँ पे हो गया 1. 1 plus 1 is result, that means sum will be 0. That means 1 plus 1 is carry is 1. Similarly here 1 plus 0, result will be 1. 1 plus 0, now sum will be 1 and carry is nothing, that means 0. If you add similarly here 1 plus 0, here sum will be 1, and 1 plus 1 is here sum will be 0 but carry will be 1. Similarly here will be 0 and carry will be 1. And last one, if you add 1 plus 1 is 0, and 0 plus 1, sum 1 plus 1 is 0, carry generated 1, so carry will be 1, and this 0 plus 1 is sum will be 1. So this will be the truth table of full adder circuitry. Okay, so we will write output expressions. So first output is sum. So write for the sum. In the sum column, you check here where you are getting a high output. This is high, this is high, this is high, and this is high. So what is the corresponding min term values or decimal. If you see for this one, what is 001 in ABC is 001, that means this is decimal 1, this is decimal 2 or min term 2. Similarly, this is 4 and last one is 7. So here I'm writing expression in a form of min term. So sigma m 1, 2, 4, 7. This is a output expression of sum. Similarly, next output expression is C naught carry out. C naught carry out, that means, you know, check here in this C naught column where you are getting high output. Here you are getting high 1, here you are getting high, here you are getting high, here you are getting high. After this, that means what is the corresponding min term value? This is min term 0, 1, 1. When the ABC value is 0, 1, 1, that means this is 3. This is 3. And similarly here is this is 1, 0, 1, that means 5. This is 1, 1, 0, that means decimal 6. So and last one is 7. So carry sigma carry naught is equal to sigma m. This will be 3, 5, 6, 7. This will be the output expression for carry naught in a form of min term. We try to solve a K-map to find simplified expression. So first K-map for output S. K-map for output S. So this size of K-map we will choose, because in this problem we having 3 inputs. So size of K-map will be 2 to the power 3 cells. That means 8 cells K-map we will choose. So we'll take 8 cells K-map. So I'm taking 8 cells K-map 0, 1, 0, 0, 0, 1, 1, 1. Cells number 0, 1, 3, 2. Now, because this is a K-map for output, similarly we also need another K-map for output C now. So I'm here main term is 1, 2, 4, 7. So in a K-map of S output, you fill in a cell number 1, 1. In min term number 2 is here present, 4, 7. So 4 and 7. If you see here, in this K-map, we try to make a group, but in this there is no possibility. If you verify from the truth table, so you find if odd numbers of inputs are going to high, that terms inputs are going to high, that terms sum is high. Okay, so we can say this output expression will be S will be A XOR B XOR C, because XOR gate having property, if odd number of input terminals are holding logic 1, that time you are getting high. If you see out of 3 inputs terminal A B C 1 1 1, all are here is 1 1, 3 inputs are holding 1, that time output is high. Similarly, if you see 1 0 0, out of 3 1 inputs are holding, one quantity is odd, so this is output is high. Similarly 0 1 0, again one input holding logic 1, so output will be 1. So odd quantity of inputs are going, if odd inputs quantity going to high, that time some output having high. So this is a property of XOR. So here will be relation between a XOR B XOR C. In another way, from the K-map, how we will try, how we will solve this is a XOR or XNOR. If you see 50% cells are filled and they are filled in alternate fashion, so this answer may be a XOR or XNOR. So how you can identify? You can identify from K-map. You see the value of ABC. If odd number of inputs are holding here 1, odd number of inputs are holding 1, that time K-map is filled by 1. That means this will be a XOR property. If even numbers are holding 1, that time K-map cells holding logic 1 or K-map cells filled by 1, that means this is a property of XNOR. So in this our problem, here is XOR properties are fulfilled. So here relation between a B, C will be XOR. So S is equal to XOR B XOR C. Similarly, we will solve K-map C naught carry out. So fill this K-map. See the expression C naught is equal to sigma m 3 5 6 7. So in cell number 3, 5, 6 and 7. Now make a bigger group. So here is 3 pairs are possible, so I'm making a 3 pairs. So I'm writing here expression for this. Now C naught will be here AB plus BC plus EC. This will be the simplified output expression for C node. Now logic diagram of this one, see. So I will make circuit diagram of this one with the help of two input XOR gate, AND gate and OR gate mixer. So see here, this is a, if you see, so this is the first stage of full adder circuitry, and this circuitry look like a half adder circuit. After this, the output of this XOR will be A XOR B, and here will be output will be A dot B. Now this output goes to the the XOR gate input, and the second terminal or second input terminal of XOR is connected to another external input C. So here you will get finally as some output of full adder circuitry, that will be A XOR B XOR C. Okay, because this is the input A XOR B, and second input is going here C. So here you will get finally A XOR B XOR C. Now here second AND gate we will take. Here the output of this A XOR B goes to here, and C input is connected here. Now this output of, if you see, this is also half adder circuitry. So if you see, so this block diagram or this first block, this is a half adder block, if you see. So similarly here, this is also half adder block. No, this is finally OR gate, and this AND gate output goes to here. This is OR gate input, and this output goes to the input of this OR gate. So this final output will be a C node carry node. So this figure is representing a logic diagram of full adder circuit. So always remember, whenever we are adding two numbers of multi-bit, that time we always prefer a full adder circuit.